Passive mode locking involves using a saturable absorber to control light inside a laser cavity. The SA allows the laser to generate short, regular pulses of light by automatically adjusting the cavity's losses based on the pulse intensity. In this case, the laser produces pulses that last for nanoseconds, driven by the nonlinear interaction between the SA and the light. This method is simple, self-starting, and doesn't require external modulation, making it efficient for generating ultra-fast pulses. A 980 nanometers laser diode was used as pump source. Subsequently, through 980 to 1550 nanometers wavelength division multiplexer, the pump energy was introduced into the cavity. A 1.8 meter length of erbium-doped fiber with group velocity dispersion of 21.6 picosecond square per kilometer was utilized as a gain medium. A polarization-independent optical isolator was used to ensure that the light within the cavity was transmitted only in one direction, that protecting the laser ring resonator from any unfavorable effect. An 80-20 coupler was then connected after the isolator to divide the optical signal, directing 20% toward the output and 80% back into the EDFL cavity for feedback. The fabricated CuPC film at 1 mm with 1 mm dimension was introduced into the cavity using a small amount of matching gel to minimize unwanted parasitic effects. The cavity length was measured to be about 6.8 meter, consisting of 0.5 meter WDM, 1.8 meter EDF, and 4 meter SMF. An additional 150 meter SMF was introduced to spark balance between nonlinearity and dispersion within the cavity to induce mode-locked pulse. Temporal activity of the generated mode-locked pulse was examined with the 350 MHz digital storing oscilloscope that uses a 7 GHz indium gallium arsenide photodetector. An optical spectrum analyzer, with an operational wavelength range from 0.6 micrometer to 1.75 micrometer, was employed for spectral analysis. A radio frequency spectrum analyzer was utilized to observe the frequency spectrum through a 7 GHz indium gallium arsenide photodetector. An autocorrelator was used for an examination of the lasing pulse width. Finally, the output power meter was utilized for average output power measurement of the generated pulses. This innovative approach leveraged copper phthalocyanines as a saturable absorber, with the SA film made via the embedding method utilizing the polyvinyl alcohol host matrix. The characteristics of the mode-locked pulsed laser are further explained here. This nanosecond mode-locked pulse was achieved at a pump power of 83.98 mW to 99.83 mW. It operates at a 1559 nanometers wavelength region. The stable pulse train was generated with no fluctuation in intensity at 349.2 nanoseconds pulse width and 1.27 MHz repetition rate. The generated pulse exhibits a high signal-to-noise ratio of 65.46 dB, proving a stable mode-locked signal. The intensity-dependent pulse characteristics shows that both output power and pulse energy linearly increased with rises in pump power. At max pump power, the laser delivered an average output power of 7.05 mW and a pulse energy of 5.52 nanojoule. Notably, this pioneering work marks the excellent potential for CuPC as an SA for producing nanosecond mode-locked EDFL. Our findings offer exciting prospects for advancements in mode-locked fiber laser technology.